Hi, everybody. I'm Skip Alzheimer, and welcome to the AV Geeks Lunchtime streaming show. I was watching the film and the comments, and I'm like, oops, I need to go. There's a delay from when it shows up on YouTube and Facebook and when it's actually happening here, so I was like, oh, I saw the end and rushed over here. Anyways, we watch old 16mm films, and that last film was a silent one from the Mogul Brothers collection. And it essentially, I don't think that's what the title was originally called. And I'm pretty sure that the Mogul Brothers did not produce that film. That they shrunk it from 35mm. Didn't do a really good job, so there was maybe some things that were cropped in the titles. So it's from some silent feature, religious short, but yeah, fascinating nonetheless. Let's watch some old 16mm films. Let's watch Middle States. Are they the flyover states? I'm not sure what they consider the Middle States. Let's watch and see. Enjoy.
The Middle States region is an unusual blend of rural and urban. It has forests of pines sweeping down to inland lakes, green pastures where dairy cattle thrive, cornfields and prosperous farms, grain elevators where the harvests are stored, stockyards crowded with cattle fattened in the corn belt. And it has crowded freight yards, great steel mills, factory production lines, and bustling cities. All these reflect the wealth of the Middle States of our nation. The Middle States form one of the 6 major regions into which we may divide the United States. There's much overlapping of these regional boundaries. 8 states are included within the region: Minnesota, Wisconsin, Michigan, Iowa, Illinois, Indiana, Ohio, and Missouri. In the late 17th century, pioneers came down the Ohio River from Pennsylvania and neighboring states. After 1800, settlers of Puritan descent began to arrive from crowded New England. Immigrants from Europe also sought homes. First came the English, Irish, Dutch. Later, the Germans and Scandinavians, who settled in the west and north. And then, with industrial growth, Italians and Slavs came to the Midwest cities. By 1840, this domestic and foreign migration had swelled the region's population to 3.5 million. By the 1950s, to 40 million, over 1/4 of the nation's population. 1/4 of the region's people work as farmers. 1/4 work in trades, services, and professions. And more than half of the region's people live in cities. As a whole, the Middle States rank first in the number of cities over 200,000 population. Certain economic areas within this region overlap its state boundaries. A heavy concentration of industry borders the lower Great Lakes. The great corn and hog belt lies across the center, including most of the soybean belt. A hay and dairy region extends from east to west. These economic areas are the key to the region's resources. The agricultural resources of the 8 states. From the extensive hay and dairy belt comes 1/3 of the nation's hay crop. In this region, where milk and its products are a major source of income, dairy farming is performed on a large scale by modern methods. Utmost care is taken, for example, to keep the dairy barns hygienic, and up-to-date equipment helps keep dairy farming on a mass production basis. From this region comes more than half of the nation's butter and more than 2/3 of our domestic cheese. Wisconsin alone produces half of the nation's total cheese. In the corn and hog belt, fertile glacial soil, abundant rainfall, and hot summer nights make ideal conditions for raising corn, over half of the nation's supply. Some of the corn goes to feed and fatten the hogs raised here, 1/2 of the nation's output. Corn that is not fed to livestock in the rural areas is shipped to mills and processing plants, where it is cleaned, hulled, and ground, and made into a variety of products, such as industrial alcohol and acetone, cornmeal, feed, and other foodstuffs. In recent years, soybeans have become an important crop raised in much the same area as the corn belt. Soybeans are used extensively on the farm for silage and are also made into products for industry. Industry is just as important to the Middle States as farming. Much of the region's prosperity comes from the industries largely concentrated south of the Great Lakes. The high productive capacity of this region was largely made possible by its vast resources of coal and iron ore. Coal, mined in Illinois and Indiana, feeds the steel mills and factories. Iron ore for the steel comes from deposits up in Minnesota. The Vermilion, Cuyana, and Mesabi ranges supply most of the nation's needs, although an increasing amount is imported from Labrador and Latin America. Shovels load the iron ore for transportation to the nearest port on Lake Superior. There, from the long docks, it's loaded onto the barges that will carry it to industrial centers on the Great Lakes, where the ore will be converted into steel. Transportation facilities play an important part in this region. The ships that ply the inland waterways made by the Great Lakes serve both farm and industry. A network of trains throughout the Middle States link distribution points with sources of supply. Fleets of motor trucks rush goods to shipping points. And there is a complex airline system. Transportation of every kind serves this region, which stands at the crossroads of our nation's commerce. To supply the needs of other regions, the Middle States send out the products both of the agricultural community and the industrial city. Its exports reflect the balance of its economy. Out of the Middle States go oil and oil products, and farm machinery and equipment from such centers as Chicago, Moline, and Peoria, on their way to agricultural areas throughout the nation. Out of the Middle States go automobiles, almost our total national production, on their way to be sold throughout the nation. Out of the Middle States go furniture and a large variety of miscellaneous manufactured goods. But the Middle States must import many things. From the Northeast, machine tools, small manufactures, woolens, shoes, and money capital. From the southeast, tobacco, coffee, and cotton textiles. From the southwest, cotton, cotton textiles, petroleum products, and some cattle and hides. From the northwest, wheat, cattle, sheep, and certain metals. From the far west, fruits, vegetables, lumber, and motion pictures. Thus, in the goods it produces and exports to other regions and to foreign countries, and in what it receives, the Middle States reflects a unique balance between agriculture and industry. The flow of goods from agriculture and industry have meant money and time to create a life rich in social and cultural opportunity. The chance to build schools in country districts as fine as those for crowded metropolitan areas. As in each of the other regions, typical patterns of rural and urban life have developed in the Middle States region. Well known for its fine lakes and other recreation areas, this region's people have a deep-rooted feeling for their countryside and a widespread interest in the arts. The work of its artists and of famous writers like Mark Twain, Sinclair Lewis, and Carl Sandburg expressed the region's distinctive tradition. And it is a region with tradition of another kind, of pioneers who blazed the early trails, and of Lincoln, raised here in Illinois, who expressed the democratic aspiration of people of all regions. That government of the people, by the people, and for the people shall not perish from the earth.
Whew. Wow, look how sweaty I'm in. It's really hot here in Raleigh and muggy, so sorry for the sweaty pit. Yeah, that's fascinating. I don't know if we call it the Middle States anymore. I think is it the Midwest? I don't know. But I've got set up behind me the film scanner, and we have a science film. And it looks like it's a series that I don't know anything about. So that's what's so great about watching films I've never seen before, is that, oh wow, what's that? Oh wow, what's that? So it is called Water Coming and Going. Typing it in as we talk. Enjoy.
When you make a face like this on the blackboard, you know what soon happens to it. A few thousandths of a gram of water slowly disappears. In much the same way, 16 million tons of water vanish from the surface of the earth every second of every day. You're going to track down what happens to all that water. To begin to find out what happens to the 16 million tons of water that disappear every second, do a simple experiment. Put 4 drops of water on 2 identical slates. Over one is a heat lamp. The other is shielded from the heat of the lamp by a wooden partition. What makes the water disappear faster from slate B with the heat lamp on it? Scientists believe the water on the slate is made up of molecules. Pretend these balls are molecules of water. The space above the balls represents air. Now, scientists believe that molecules are in constant motion. Turn up the speed control. The motor connected to the plunger makes the balls move. Now the balls represent the water molecules in motion on the slate. By now the water has disappeared from both slates. As the experiment is set up again, get ready with a sheet of paper and a pencil. Write the numeral 1 near the top of the sheet. Remember, the water molecules on the slate are moving. Now here's a question for you. Is the water disappearing more rapidly from slate B because the molecules, on the average, are slowing down, staying at the same speed, or speeding up? Next to the numeral 1 on your paper, write the phrase that best describes what you think is happening to the molecules of water on slate B. You'll write one of 3 possible answers: slowing down, staying at the same speed, or speeding up. According to scientific theory, as heat energy is added to the water molecules, they begin to move faster and faster. The speedier ones fly away from the surface of the water and up into the air, becoming molecules of a gas, water vapor. The correct answer to question 1 is speeding up. The water molecules on slate B are being speeded up by the heat of the lamp, and that's why they're evaporating faster. Make a new water face and cover it with a sheet of glass. Notice the evaporation slows down because the glass keeps the air from flowing over the slate and carrying away the factor molecules. Shine a heat lamp on the slate. The dark slate absorbs the heat energy. The transparent glass absorbs little of the radiant heat coming from the lamp. Now the face is almost completely evaporated. The water molecules are in the small amount of air between the slate and the glass. This time the water has gone from the slate, but watch. Now it's on the underside of the glass. Ordinarily, it would evaporate very quickly, but it will be held for you to answer question number 2. As the water molecules collected on the glass, were they slowing down, staying at the same speed, or speeding up? Next to the numeral 2, write down the phrase that best describes what you think happened. The molecules were slowing down, staying at the same speed, or speeding up. Here are the imaginary water molecules again, zooming around as a gas in the air between the slate and the sheet of glass. Turn down the speed control, in effect lowering the temperature. The molecules lose some of their energy. As they slow down, they bunch together and become molecules of a liquid again. The balls were pulled down by the force of gravity, but assume the plunger is a cool surface in this position. As the molecules touched it, they would lose their heat energy and collect on it like this. If the cool surface were on this side, the molecules would condense into a liquid on this side. If the cool surface were a sheet of glass above a slate, then as the molecules of the vapor lost their heat energy, they would slow down and condense into tiny droplets of a liquid on the underside of the glass, directly above the slate. The correct answer to the second question is slowing down. Molecules of water vapor are slowing down when they become molecules of a liquid. This process is called condensation. As the water molecules on the glass absorb heat from the glass and the air, they pick up enough speed to evaporate, and the wet face that disappeared from the slate to reappear on the glass disappears again, this time for good. You've seen this happen many times. These water molecules are being heated up so fast they form bubbles of gas under the surface of the water. The bubbles float to the top, and the gas molecules escape into the air. In other words, the water is boiling. Boiling is very much like evaporation. In both cases, a liquid is changing to a gas. But in boiling, the change takes place very quickly because the heat energy is supplied at a greater rate. So the water in the flask corresponds to the water face on the slate, and the large glass tank corresponds to the sheet of glass. You probably know what's going to happen. These are the tiny droplets of water that formed when the water molecules condensed on the cooler glass. But now a new thing happens. Watch. You probably know what this is called. So question 3 should be easy. When drops of water fall like this, is it called inclination, precipitation, or concentration? Write down the name for what is happening. Inclination, precipitation, or concentration. Here are the balls again, representing molecules of a gas. But this time they're being trapped by a collar at the top, losing their energy and condensing into a water droplet. Now, they're not shaped much like a droplet, but that's what they're supposed to represent. As more molecules are trapped, they join up to form a bigger droplet. When real droplets get heavy enough, they don't need a hand. Gravity pulls them all down as drops of water, falling headlong as from a cliff, which is what the root of the word precipitate means in Latin. And that's the correct answer to question 3. Now combine the 3 experiments. Do them all at the same time inside this transparent plastic box. Take a good look at it, because later you'll draw a diagram of it. One end is higher than the other. There's a sloping roof. At the bottom is a layer of soil that leads to a shallow pool of water. Above the water is a heat lamp, which is turned off at the moment. The temperature over the water is 20 degrees Celsius. From the side, you can see that the heat lamp is much lower than the highest part of the roof. At the bottom of the roof is a small trough. You'll see what it's for later. The other thermometer near the top of the box reads 20 degrees also. On a new sheet of paper, get ready to make a simple diagram of the box. Something like this is all you need to draw. The angled roof, sloping land, water, heat lamp, and thermometers. Here's a close-up view of the lower section of the box. One last look at the entire box so you can finish your diagram. Below your diagram, write these 3 letters. E for evaporation, C for condensation, and P for precipitation. When the heat lamp is turned on, observe what happens in the box and put the three letters E, C, or P on your diagram where you see evaporation, condensation, and precipitation taking place. Ready? By now, the temperature over the water is 47 degrees, while the thermometer at the high end is 40 degrees. This is your last chance to put letters on your diagram. Does your diagram look something like this? Now, you may not have all your E's, C's, and P's in the same places because evaporation was taking place throughout the box, but in the area of the heat lamp, water was evaporating faster and in greater volume than anywhere else. Condensation took place on the sides and the roof of the box. Precipitation came later, drops falling down the sides and down the roof. Drops of water formed at the end of the trough because it collected the precipitation from the roof. Now add an arrow to your diagram like this. The heat from the lamp speeded up the water molecules. The warm air rose, carrying the evaporated water vapor with it. As the air cooled, the water molecules slowed down. They also slowed down when they touched the cooler sides and roof of the box. Condensation took place. Draw in the second arrow. The water droplets combined. When they became heavy enough, they ran down the sides and roof of the box as precipitation. Draw in the third arrow. The water flows down the land back to the pool. There it evaporates and begins its coming and going all over again. What you've just diagrammed is called the water cycle. The huge box of air called the atmosphere surrounds the entire Earth and is 20 miles deep. In it, the water cycle is repeated over and over again, day after day and year after year. It begins with the heat of the sun. water evaporates into the air from oceans, lakes, ponds, puddles, and from hundreds of other sources all over the earth. As the warm air rises, it's cooled. The evaporated water in it condenses to form clouds made up of billions upon billions of tiny water droplets. When the droplets form close to the ground, it's called fog. Sometimes the water condenses into a thin cloud of ice crystals in the extreme cold at high altitude. Other times the supercooled moisture high in the air condenses into droplets when disturbed to form a vapor trail. When conditions are right, the moisture in the air can condense directly on the cooler ground and trees, covering the landscape with frost. The droplets within clouds continue to become larger and larger. Eventually, they fall as a gentle rain, or a shower, or a downpour. When the air itself is cold enough, the water can crystallize and fall as snow. As the water begins its journey on the land, evaporation begins again. Even in winter, molecules evaporate from the cold water and even from the snow and ice. The water that has not evaporated during the journey can finally become part of a lake or an ocean, only to evaporate there in huge quantities. New clouds form. That's how water comes and goes. The water cycle is a complicated journey that never ends.
Oh, wow, you guys did not like that, Phil. Was it because it was a pop quiz kind of thing, or was it because the color had faded to a muted grayish red? Was it because it was so static and so tedious? What was it that made it so bad? And I have to say that the more boring a film gets, the funnier you guys get in the comments. And so I appreciate that. Precipitation trophies. All right. So I made a change to donations here on my little info box. The Apple Shop Film Archive, which is based in Whitesburg, Kentucky, suffered a miserable flood. And their film vault was basically submerged. And so there's a bunch of archivists that are going there. I unfortunately have other things going on and I can't go there in the first pass, but maybe another pass. But in the meantime, I'm donating, and you can donate at appleshot.org. They're a nonprofit, so they need help. I mean, they basically helped filmmakers document Appalachian culture from the 70s up to now, and all the aspects of Appalachian culture. And a lot of those materials got flooded. So they're working on ways to wash the films that are still wet, to get the mud and the gunk out, and so the emulsion won't stick together. They're putting things in climate control so that they have more time to work with and process the films and get them cleaned. But that takes time and money. So that's what I'm doing right there. All right, whose fault is it? I think it's Sam Andreas' fault.
Near San Francisco, urbanization has plowed over the fault and nearly obliterated its trace. But the fault becomes clearly visible in a radar image of the San Francisco Bay Area. Muscle Rock, where the fault dips into the sea. San Andreas Lake. The Central Fault region, where deep, straight valleys mark the fault's path. To the naked eye, the San Andreas Fault is most evident on the barren flatland of Central California's Carrizo Plain. Here, where there is scarcely a trace of civilization, the fault is visible as a thin, well-defined line of deformation, crossed by an occasional dry stream gully. In some places, the fault is traced by the foot of a gently sloping hill, or by a shallow depression in the landscape. In others, it is more obscure, its presence marked only by a primitive road. More dominant features can be seen farther south on the Carrizo Plain, where a few desolate farmhouses dot the land. The fault appears as a thin valley that cuts across the general slope of the plain. Where the terrain is steep, the centuries have etched their mark into the land with deep, eroded channels that descend from the vicinity of the fault line. Altogether, the San Andreas Fault slices through some 1,100 kilometers of California countryside. From Mexico, north through the San Francisco Bay Area, and on into the sea. In many places, it is not a single fracture, but a complex zone of branches called the San Andreas Fault System. On the southern portion of the fault system, east of the Salton Sea, rocks have been squeezed and fractured by pressure in the fault zone. As evidence of its powerful motion, the fault has left slick, highly polished rock surfaces. Evidence of this sort is often found where road construction has torn away part of the Earth's surface. Near the town of Gorman, a road cut exposes a mass of granite. Granite is often used for building. Normally, it is a strong, durable rock. But in the fault zone, this granite has been crushed almost to a powder. The softening is the result of millions of years of grinding action. Farther south in the fault zone, a highway passes through terrain that has been forced upward by pressure around the fault. Where the road intersects the fault zone, rock on the face of the road cut is contorted and twisted by the compression of two huge sections of earth squeezing together. Changes like this take place very slowly. The awesome forces that come into play are rarely experienced directly by man. But proof of motion along the fault is here, in the geologic record of the land. One of the most dramatic examples of this proof can be found in the Carrizo Plain, where the dry gullies of drainage creeks descend to the fault line.
These streams do not flow in a straight line. At the fault, they veer sharply to the north. The offset of this stream is the result of motion along the fault. This model shows how the offset was produced. Land on the western side of the fault has been moving slowly northward with relation to the eastern side. Where the stream crossed the fault trace, this horizontal motion diverted the flow. Further motion completely interrupted the stream's path. Eventually, the waters of the stream eroded a new path into the land. But again, the new stream was offset by movement along the fault. Today, the stream is displaced about 20 meters to the right where it crosses the fault line. This offset is probably the result of several hundred years of fault motion. In geologic terms, several hundred years is not a very long time. Much greater displacements, involving much longer periods of time, have occurred along the San Andreas Fault. Over millions of years, this movement has been sufficient to displace huge blocks of earth. In this creek bed, two different types of rock lie side by side. The rock on the right, a few thousand years old. The fault is evident between the sections, where a soft, pliable substance called fault gouge has been formed by the Earth's relentless squeezing and grinding action. Matching of rocks on opposite sides of the fault zone gives an indication of how much the Earth has moved and how long it has been moving. A sample of an unusual and easily recognizable type of rock is selected from the western side of the fault zone in central California's Fraser Mountains. In the desert of Southern California, an outcrop of identical rock is found in the Orocopia Mountains on the eastern side of the fault. This suggests that movement along the fault had separated one mass of rock into two, probably over a period of about 20 million years. The separation is shown by the points marked A on this map. The matching rocks are about 300 kilometers apart. Geologists have mapped many distinctive rocks that seem to have been separated by fault motion. The oldest rocks are the farthest apart. The motion that occurs along the fault takes two distinct forms. One is the very slow, nearly continuous movement that geologists call creep. This fence has been offset by creep. The motion is slow, but persistent. Normally, creep can be observed only through its effects. In Hollister, California, the Almaden winery sits directly atop an active branch of the fault zone. Inside one of the winery warehouses, reinforced concrete walls and floors are slowly being pulled apart by creep movement along the fault. This simple model shows how the displacement takes place. The slow movement of creep can be measured. Here, the Earth is moving at an average of about 13 millimeters a year. The other form of fault movement is sudden and sometimes violent, the earthquake. Severe earthquakes contort and destroy man-made objects of all descriptions. In California, they often originate along one of the branch fractures that make up the San Andreas Fault system. The sudden power of most California earthquakes is released less than 12 kilometers below the surface of the Earth. The shock waves that radiate from their centers can damage buildings at distances of 150 kilometers. The amount of energy released varies widely. The energy of this earthquake was less than 1% of that released near San Francisco in 1906. It is obvious that earthquakes are closely related to movements of the Earth's crust. Geologists believe that the San Andreas Fault may be the border between two huge portions of the Earth's crust called plates. The Pacific Plate, which includes the western sliver of California, is moving slowly northwestward with relation to the North American plate. This model will show how the plates move. The white lines are for reference. Plate motion in the model causes the buildup of strain. The strain is released in sudden slips. In the same way, strain builds along the San Andreas Fault. Generally, friction between plates causes the locking of rocks along the fault. When the locking rocks give way, the strain built up over long periods of time is released in a matter of seconds. The result is an earthquake. To learn more about when and where earthquakes might occur, geologists study many kinds of movement along the San Andreas Fault. At present, few geological phenomena are analyzed by more scientists or monitored by more sophisticated equipment. Near Bear Valley, south of Hollister, one of hundreds of tilt meters measures the slope of land that is warped by elastic strain near the fault zone. Even the slightest change is recorded by the meter. It is so sensitive that it reacts to the earth wave created by the footsteps of an approaching man. The fault is also studied with laser beams that measure horizontal movement over long distances. A narrow, intense beam of light is aimed from one side of the fault to a reflector 10 kilometers away on the other side. Meanwhile, a helicopter flies close to the line of sight to collect atmospheric data that could affect the readings. The travel time of the light is recorded and corrected for the atmospheric distortion measured from the helicopter. Any motion along the fault is detected as a change in the shape of a laser triangle. Minute fault movements can also be measured directly with sensitive creep meters. This pit is the terminal point of an underground wire that stretches diagonally across the fault. If there is any movement, the wire is pulled. The displacement is measured and recorded. Earthquakes, too, are constantly recorded. Hundreds of minor tremors occur along the fault every year, most of them so slight that they can be detected only by very sensitive instruments. Seismometers on the fault zone measure these tremors and relay the information to data collecting stations by radio. This information, translated to seismograms, provides a continuous picture of tremor activity in the fault zone. Some types of earthquake research can be conducted under controlled laboratory conditions. In this experiment, a sample of rock is subjected to shear stress. The object is to duplicate the kind of locking and slipping behavior that is characteristic of rocks deep in the San Andreas Fault zone. Through electronic sensors, tremors in the rock sample are measured. They result in seismograms that closely resemble those produced by real earthquakes. This experiment can be repeated while varying the pressure, temperature, and water content of the rock. Geologists can thus learn if any of these factors are important in determining when and where earthquake activity may occur. At the National Center for Earthquake Research in Menlo Park, California, data is received from hundreds of instruments all along the fault system. Statistics on tilt, strain, creep, and tremor activity are collected and stored. Current conditions are monitored, and data is fed into computers. The computers combine data compiled over many years and translate it into visual form. Month by month, tremor by tremor, a computer provides a graphic readout of seismic activity in the San Francisco Bay Area. A close look at this readout shows very little tremor activity in the northern portion of the fault system. The fault appears to be locked. Elastic strain is probably building up. Geologists estimate that the strain in the fault's northern reaches is already approaching the level that preceded the devastating earthquake of 1906. If that earthquake were to be repeated today, its tragedy would be increased manyfold in modern California. Geologists and engineers have tried to estimate the effects of such an earthquake. In one estimate, property damage exceeds $24 billion. More than 100 bridges and freeway overpasses collapse. 10,000 residents of the San Francisco Bay Area are killed. The San Francisco Bay Area is today the home of more than 3 million people. Another 7 million are centered around metropolitan Los Angeles. It has been estimated that by the end of the century, 1/7 of the United States population will live in the state of California. Most of these people will be living in the shadow of the San Andreas Fault. Some geologists say that California's next major earthquake could come tomorrow. Others say it won't come for 100 years. But all agree that it is coming. The question of when and where the next major earthquake will strike is of great importance to the people of California. But the San Andreas Fault and the motion along it are only small parts of a much larger story. Somewhere, deep within the planet, an unknown force is causing huge sections of the crust to move, gradually rearranging the surface of the Earth. What is the nature of this force? Where does it originate? And what effect will it have on the geography of the Earth over millions of years of geologic time?
Okay, so that was a little ominous. Let me end this. We're going to go a little bit over, but that's fine. This is called People Soup, and I don't know if I've shown this or not. I don't have any notes in my lunchtime shows that I've shown this, but this is a film made by Alan Arkin, and it's fascinating. It's really good. So enjoy.
Wish I had the wings of a dove. Wish I had the wings of a dove. I would fly, fly away.
Oh, hi, Adam.
Hello.
What you doing?
Nothing.
Can I watch?
Nope.
Is it going to be another experiment?
Who wants to know?
Me wants to know.
Maybe it is and maybe it's not.
Maybe it is, maybe it's not. Now,
Nope.
what's it going to be?
Stuff?
Government stuff?
Nope.
Spaceship stuff?
Nope.
Medicine?
Nope.
I give up.
It's animal serum.
What's animal serum?
It's certain properties without which the universe and eternity regards for human beings.
What you looking for?
The applesauce.
I know where it is.
Where is it?
Why should I tell you? You won't let me have.
Come on, Matthew, tell me.
Nope.
You're a rat, Matthew.
I know you are, but what am I?
You're not going to play my drums anymore.
I don't want to play your drums anymore.
Damn it, Matthew, didn't I help you carry that damn pool table all the way up to your room yesterday?
So what? You're the one always using it. I can't even play pool.
And you can forget about using my TV also.
Then I'm not paying you the dollar I owe you.
You're a rat. You weren't going to pay it anyway.
And now I'm really not going to pay it.
If you give me the dollar, I'll let you help.
I haven't got a dollar.
What do you got?
2 dimes.
Give me the 2 dimes.
You're crazy. I'm not going to give you all my money.
1 dime, then.
Okay. Here.
Thanks.
What should I do now?
Get the applesauce.
Hey, Mars, the new hiding place.
Where is it?
Find the applesauce.
What'd you find there?
2 chocolate grams.
Give me one.
Okay. What should I do now?
Stir it. It's done.
What do we do now?
Has to sit for 10 minutes. Come on, let's fight.
Oh, God. God, you sat on my stomach. Come on. Enjoying the neighborhood football game? You got it. I got. Get
Okay, let's go back in the house now.
Okay.
It's done.
Ugh, what do we do with it now? Throw it out?
No, now we gotta drink it.
Drink it? What do we have to drink it for?
It's an experiment. That's what you do with experiments.
Smells like garbage.
Medicine smells like garbage and it makes you healthy.
I'm already healthy.
This isn't medicine.
Then what is it?
You'll see. Go on, take some.
You're crazy. That stuff will kill you.
How can it kill you? There's nothing but pure food in there.
You do it first.
I can't do it first. I have to watch the effects.
How much do you have to take?
Just a little. Stick one finger in and lick it off.
This enough?
Plenty.
What if I get sick?
You can't get sick. There's bromo salts in there.
Well, here goes.
What does it feel like?
Well, it's not so much it goes down and you can taste the chocolate graham. Makes it feel like... What happened?
You turned into a chicken. I thought you'd be a squirrel.
Let me see what I look like. Get a mirror. I'm a pretty ugly chicken boy.
Gotta get used to it.
I don't want to get used to it.
Why? What does it feel like?
Skinny and I can't see good.
What else does it feel like?
I told you what it feels like. Now get me out of this chicken.
First, tell me what it feels like.
Get me out of here.
Matthew, what are you afraid of? This is an important experiment.
Wait till Mom sees what a mess I am. Boy, are you gonna get it.
What a sissy. You're ruining the experience of a lifetime. I'm disgusted with you.
Damn you, Adam, change me back. Ma, look what Adam did to me. Ma! It's a good thing you fixed me, boy. You would have really gotten it from Ma if she'd come home and I was a chicken.
Oh, what a queer. I hope I turn into an alligator. I'll bite your head off. What am I?
You're a sheepdog.
No, come on, what am I?
You're a sheepdog.
Crap.
Can I have a ride?
What, are you crazy? You want to kill me?
I just asked. What you changing back for? You're a nice dog.
Shut up. Come on, let's go get some ice cream.
Want to make some more of that stuff tomorrow?
Not the same stuff.
Want to make something else instead?
Maybe.
Atom bomb?
Okay. But we have to get some more applesauce.
All right, there was some salty kid language in there that I did not expect, but a great film nonetheless. The kind of the transformation of the kids into the animals are just, they're kind of a little nonplussed by it. I mean, Matthew was a little irritated, but I think he would have been irritated if Adam had done something else to him that hadn't turned him into an animal. So, yeah, interesting find, man. This is why we watch these old films, because we don't know. We don't know what's in them. And where else would you see that film? I mean, you know, they're not going to probably bring this up on a Alan Arkin retrospect. So that's why we do what we do here. And that's why we appreciate you guys tuning in. If you like what you saw, please hit the thumbs up button, smash the like button, subscribe, share. You can also, if you're jonesing for some more films, you can go to avgeeks.com, where we have a 24/7 channel that just shows older lunchtime shows, but also other things that we've digitized. And so that's a great place. Normally I ask for coffee, but I'm asking, instead of buying me coffee, help out Apple Shop Film Archive, which was basically underwater last week due to flooding, and is still dealing with some flooding, which is very frustrating. Appleshop.org/donate. Any amount, even $1, I think would help their efforts at this point, and getting the word out. There's some really heartbreaking photos that I could send you of some films that are covered in mud and stuff, but I'm gonna not do that. So the other thing is, I'm gonna be on the road for about a week, so I'll be joining you at lunch, with pre-recorded shows. I have some interesting adventures ahead, and hopefully I can capture some of it on my phone and share it with you. But I will see you. I'll certainly check in on the comments and all that. Try to do that every day if I can. Everybody take care, and we will see you soon. As always, please rewind, love each other, and join us tomorrow.